Okay, hey guys, welcome to this session. So today I'll be presenting our work on robust submodular minimization. So the keywords here are robust submodular minimization with applications to cooperative modeling. And this is the ECAI 2020 full paper. And my name is Rishabh Iyer. I'm assistant faculty at University of Texas at Dallas. The key problem over here is we'll be talking about a class of combinatorial optimization problems with applications in machine learning, right? So essentially, what's combinatorial optimization? So essentially, the problem here is that we want to select amongst a set of items. So the set could be uh, a, s- a s- a set of items like this. So we have a set A and we take a subset V of items, or we might have graph problems where we want to where we want to select a subset A from the edge set, right? Or select a subset of vertices and we select a subset A from the vertex set, right? So all of these are kind of combinatorial optimization problems where we are basically selecting either a subset of items or a subset of edges or vertices from a graph. So combinatorial optimization has been studied typically in applications like scheduling, telecommunications, social networks, etc. But they are becoming increasingly prevalent in machine learning, right? So they have been applicable in kind of inference problems in like graphical models and networks, problems like data selection and various assignment problems, image correspondence, peptide identification, data summarization, and so on, right? So the kind of standard most typical way of modeling this would be to do what is called as a linear cost combinatorial optimization, right? So what we mean by linear cost here is that we have a combinatorial problem, like for example, finding cuts in a graph, right? And an application of this is image segmentation, right? So image segmentation, you have kind of the foreground, right? And then you have the background, and then you want to find cuts basically from the foreground and background, right? Other application is image correspondence, where you have sets of pixels over here and you want to match pixels, right? So similarly, peptide matching is an assignment problem. Connecting news articles is a minimum path problem. Robot drone orienting again is a minimum path problem. And then things like active learning, etc. over graphs. This has been studied as spanning trees, right? So a lot of applications kind of involve linear cost combinatorial problems. But what are the limitations of linear cost models, right? So linear cost models do not model interactions amongst the nodes, right? So we have set of nodes over here. Typically, the problem is as if you have a sum of either edges or sum of nodes, right? So we want to first model interactions, and these interactions are cooperative in nature. Secondly, this is not oftentimes robust to noise. So we want to somehow model robustness, right? So this will be the key aspect, is that we'll try to model cooperation and robustness. So the question is, how do we model cooperation and robustness, right? So the first is to kind of define nonlinear costs over graphs, right? So we have some kind of an interaction amongst pixels or some kind of interaction over nodes here in this peptide matching and so on, right? So this is one way we can model interaction. And the second is we want to do basically robust optimization, right? So we want to consider many potential distributions and we want to be robust on these distributions. So we'll see exactly what we mean by cooperative and robustness in the next few slides. So the first question is, how do we model interactions, right? So a kind of natural model of defining interactions is via the notion of information functions, and particularly the kind of concept of submodularity that I will define, right? So given a set of images, for example, over here, I want to model the information content in images, and I want to kind of basically take into account the interactions amongst images, right? So what are natural ways of modeling interactions? So for example, I have two sets over here. This is a set S1 and a set S2, and the subset S1 is a subset of S2, right? And in some sense, the gain of adding a new image, right, over here, this is the new image. The gain of adding a new image is actually more in the case of S1 than in the case of S2, right? Why is that? Because there is in some sense an interaction between these two images, and a very similar image is already present in S2. So this new image actually has a negligible gain when adding it to S2 compared to adding it in S1. So this is one way of modeling interaction which is cooperative in nature. So to make this more concrete, we'll define the notion of submodular functions, right? So submodular functions basically have this kind of notion of diminishing returns, that the gain of adding an element shrinks as the context of the set grows. So this is what this inequality says, and this is an example of an instance of a submodular function. So it turns out that several natural models of information are actually submodular functions. Many of these combinatorial kind of aspects, right? So modeling things like coverage, diversity, complexity, information content in a set of random variables, representation, as in what you want in kind of k-means clustering to find the centroids. There's a representation and cooperative costs. All of these are instances of submodular functions. So very quickly, now we'll come to the main kind of problem of this work, right? So we start off with the linear cost graph problems, and this is kind of textbook material. So this is what has been known and well studied as basically in the combinatorial optimization literature, right? So we can go one step above and define extension of this with submodular functions, right? So we have instead of just additive cost over here, we have a submodular cost over the same constraint, right? So this can be, for example, this is a set of edges, for example, being ST cuts, ST paths, assignments, edge covers, vertex covers, and so on, right? A kind of flip version is to make this robust, right? So this is the robust version of this, and this is where instead of having one weight, I can have multiple weights, and then we form this as a min-max problem, right? So the reason for this is that we actually want to study multiple potential models, WI, right? And we want to minimize the worst case amongst these multiple models. So this is basically the robust formulation over here. And in some sense too, we want to make this robust as well. And this will be the focus of this talk. So we'll in some sense complete this matrix. So this work is textbook work. This has been studied in several papers as listed down here. It turns out that the linear cost versions of these also have been studied in several papers. And in this work, we study the robust submodular graph optimization problem. So this will be the focus of this work. All right, so it turns out that this problem, even without the robustness, actually is very hard. So these are all polynomial hardness results, right? So this is pretty pessimistic. So in some sense, the goals of our work and the goals of this paper is, given the fact that the hardness bounds are actually polynomial in the worst case, the first question is, can we provide scalable algorithms, right? So can we obtain algorithms that are scalable and have bounded approximation factors? And well, we know that its worst case is polynomial in the worst case. So can we provide improved bounds for certain subclasses? So we will actually study these two questions in the robust problem context in this work, right? So uh, briefly detour, and very quickly I'll actually introduce the kind of main machinery here. I don't have much time, so I'll go over it very quickly. The main machinery actually uses the notion of semi-gradients of submodular functions. So just like convex functions have kind of linear lower bounds and concave functions have linear upper bounds, right? It turns out that with submodular functions, we can actually define similarly linear or modular upper bounds and lower bounds. So it turns out that there is actually work by several papers, including our paper from 2013, where we can actually define subgradients of a submodular function and supergradients. So this is in some sense in contrast to known results from continuous optimization, where you can't really define both subgradients and supergradients. But it turns out that in the discrete world, we can actually define subgradients and supergradients. So again, I won't go into a lot of detail, but it suffices to say that you can actually define these two gradients. And the whole idea of the majorization minimization framework, right, which is the main kind of scalable algorithmic framework which we shall use over here, is to iteratively, sequentially define upper bounds of the submodular function as proxy functions, right? And we'll do this iteratively. So we start with a point over here, and then we will minimize the upper bound, obtain the set, say this is S1, we obtain the set S2, again we minimize the upper bound, and so on, and obtain S3 and so on. So we repeat this until convergence. So the main idea is that we use upper bounds and iteratively solve linear cost graph problems, right? So this is without the robustness. In the case of robustness, it turns out we can achieve a very similar algorithm, but we iteratively solve the robust linear cost graph problems. So how do we solve the robust linear cost graph problem? So it turns out that there are existing algorithms, but they actually only work when k is constant, right? So we use somewhat of a heuristic approach, which actually has bounded approximation factors, where we approximate the robust function with a function of this form. And this can actually provide an approximation algorithm for the linear cost version. And then we can actually similarly extend this to the robust version where we have a problem like this, which is the min-max problem over FIs. And then we can replace this with sequential linear upper bounds as WIs, and then we solve this linear cost version using the algorithm suggested, right? All right, so one more small detail is that for subclasses, just like in the case of continuous optimization, you can provide quantities like strong convexity, Lipschitz continuity, and so on. We can provide similar factors, and this factor is known as the curvature. So the curvature, in some sense, models how close to linearity is the submodular function. And it turns out that many submodular functions in practice actually have bounded curvature. So this is good news because what it means is that many of the polynomial approximation factors actually can be reduced to curvature. So I'll give you one example, right? So this bound, for example, if f is square root n, so square root n is a standard bound that oftentimes comes up as an approximation guarantee. Then the curvature based bound is actually something like this, which is square root n over 1 plus square root n minus 1 times 1 minus kappa f, which is actually 1 minus kappa f if kappa f is bounded. So what that means is that if we have a bounded curvature, we can actually get bounded approximation results which are not polynomial anymore. So this is one of the other contributions of this book. So, okay, very quickly, we'll go over some real world experiments. And here we look at cooperative matching for image correspondence. And the idea of cooperation is actually to look at groups of pixels and model cooperation amongst groups of similar pixels. And it turns out that actually the robust version works much better than just the submodular cost problem and the linear cost problem. All right, so with this, I'll actually end the talk. I'm sorry I went a little bit over, but thank you so much for your patience.